All right, welcome. Let's do some double integrals. Okay, so maybe you were in my class and you've done the AP exam. I showed you how to take a double integral. You thought you were done integrating, but no, you're not. Okay, so probably did number 11 for you in class, but just in case I didn't, I'm just going to go off of these problems, do all of these. And if I already did 11 for you, well then feel free to skip ahead in the video, I guess. Okay, the key is we're going to block off the inside integral, do it first, and then work our way out. Okay, we can do this. Okay, take an antiderivative for x plus y with respect to y. Okay, so you're thinking about this kind of the way you think about a partial derivative. You're thinking x is a constant. So the antiderivative of a constant with respect to y is that constant times y. And this would be 1/2 y squared, right? As y runs from 0 up to 2, and then we're still going to integrate that from 0 to 1 dx. Okay. And then I actually need to plug this in and subtract. So when y is 2, I'll have 2x plus 2. When y is 0, I'll have 0. So this is just going to be the integral from 0 to 1 of 2x plus 2 dx. And, well, now this is going to be much easier because I can anti-differentiate with respect to x. Plug in 0 and 1, and that's going to be 1 plus 2 is 3, minus 0, well, that's just 3, right? We can do this. And double integration, very much like single integration, especially if you know the process. So I'm going to just work that one. I don't think I'm going to copy number 13. No, but you can just see that at the top of the screen. And I'm going to take an antiderivative with respect to x first. And so that would be 1/3 x to the third minus 2y squared times x, as x runs from 0 to 4. Okay, 4 to the 3 is 64. So I've got 64 thirds minus 8y squared. But then when I plug in 0 for x, I'll get 0 and 0. Right? So this is what I'm integrating with respect to y from 1 to 2. And this I can anti-differentiate. Minus, okay, if I increase the power by 1 and divide by the new power, well, that will be 8/3 of y to the third. And we're letting y run from 1 to 2. So this will be 128 over 3 minus 8 times 8 is 64 over 3. Minus, okay, when I plug in 1, that's 64 over 3 minus 8 over 3. Okay, so it looks like this one's maybe positive 8/3. I don't know. Okay, it looks like it, but I don't want to say the wrong thing. All right, number 15. Y cosine x dy and then dx. So with respect to y, cosine x is a constant. So antiderivative is 1/2 y squared, and then so I'll have that cosine x there. As y runs from 0 up to 1. Okay, well, this is best case scenario, right? Because I'm going to say this is all right. 1/2 of 1 minus 0. Okay, so I have 1/2 cosine x getting integrated from 0 to pi over 2. Okay. And we can anti-differentiate this. That's going to be 1/2 of the sine of x, as x runs from 0 to pi divided by 2. Sine of pi over 2, I know that's 1. Sine of 0 is 0. Okay, that's half. Okay. Let's look at this one. I'll start. All right, number 17. Is that? Yep. Okay, this one's got variables on the inside. I'll kind of draw you a picture to show you what this means. So first I'm going to anti-differentiate with respect to y. Okay, y is running from 0 up to the sine of x. And so to just draw you a picture, we're integrating, it's a surface that sits over some region, kind of like you can see in these bad drawings there. Okay. So what's really happening is that x is going from 0 to pi, and y is running from 0 to sine x. Okay, so I know what y equals sine x looks like. Okay. Let's see, more or less like that. Whoops. Okay, did the best I could. Okay, but y is running from y equals 0, that's the x-axis, up to y equals sine x. And x is going from 0 to pi, and pi is that first 0 here. And so this is the region that I'm integrating over. It's not a rectangular region like the rest of them we did. And if you want more information on this, you just need to take the multivariable calculus class, right? If you're interested at all, then I think you would like it, okay? Because it really just plays off the strengths that you have from this year. Okay, but anyway, this is the region that we're integrating over. We've got some sort of surface that's z equals 1 plus cosine x. Not really sure what that looks like. I'm sure it's pretty wavy. That happens to sit over that. It'll have some amount of volume. That's what we're computing here. Anyway, all right. So sine x plus sine x cosine x minus, okay, well, when y is 0, that's just both of these things are going to go 0. So this is the integral from 0 to pi. Okay, now, I'm not going to do the wrong thing. Somebody asked me about this one in class, and I showed them a trig identity. I showed them sine of 2x is 2 sine x cosine x. I got something better for you that was suggested to me by a student in my 3rd period class. And what that's going to be is just to find an antiderivative for sine x cosine x dx. Okay, yeah, I'm still there. I would say block this off, right? Let u equal sine x. Then du is cosine x dx. So this becomes the integral of u du, which is 1/2 u squared. So I know that this is 1/2 u is sine x, 1/2 sine squared x. That was slick. Okay. I doubt the person that showed me this is watching because I bet he's already done all of them. But if you are, thank you. That was really nice. Okay, so I've got an antiderivative for sine. That's negative cosine. And then an antiderivative for this guy is 1/2 sine squared x. Okay, and then we're going to let x run from 0 to pi. Okay. Well, sine of pi and sine of 0 are both 0, so this thing doesn't really contribute anything. So this is going to be negative cosine pi minus negative cosine 0. Okay, so that's negative of negative 1 is 1, plus another 1 is equal to 2. Okay, that was number 17. Okay, 22. Got going here. Antiderivative for 10, we can do that with respect to x. That's 10x plus 2/3 x to the third. 2y squared is constant with respect to x, so I'll just tack on an x and let x run from y up to x equals 2y. Okay, just to show you what region this would look like. X equals y, we know what that looks like. It's y equals x. And x equals 2y, that's y equals half x. So that would be like this, just half as steep. And x, no, wrong one. X is running from y to 2y. Y is running from 0 to 2. So oh, pardon me. I see what's going to happen here. This needs to extend much farther. And yeah, you can't barely even see that. And so I was like, that doesn't look quite right. And so if y ends at 2, then we would need that. And this is going to be the region I'm integrating over. Okay. Now, what was I thinking here? Oh, yeah, we're ready to go. We're ready to plug in x equals 2y. So that's 20y. X equals 2y. So then if I cube 2y, I'll get 8y to the third. So that's 16 thirds y to the third. Okay, when I plug in 2y for x, I'll get 4y to the third. minus, and when I plug in y, I'll have 10y plus 2/3 y to the third and 2y to the third. Okay, so when I combine all of these, I would have, that would be 12, so 28 minus 2 is 26. Be 20/3. Hold on, I don't like that. Okay, 4 minus 2 is 2. 16/3 minus 2/3 is 14/3. Yeah, 20/3. Okay. Y is running from 0 to 2. So I anti-differentiate. Plug in 0 and 2 and subtract. So 10 times 4. And then I would be subtracting 0, so that'll be it. Okay, number 22, number 27, and number 33. Okay. Oh, getting in a polar variable. I like that. Okay, that's definitely something you would be interested in computing in a multivariable calculus class for reasons that I will leave to whoever is going to teach you about that. Okay, now r d theta. Okay, an antiderivative for r with respect to r would be 1/2 r squared. We'll let r run from 0 to r equals 2 cosine theta. Okay, so I have, when r is 2 cosine theta, then that would be 4 cosine squared theta divided by 2 is 2 cosine squared theta. And we're going to integrate that from 0 to pi over 2 d theta. Okay, now this is the type of antiderivative that I've shown you how to do before. You need to use a reduction of power formula, and if you want to do that by hand, I will copy that in here real quick. And you could just take it the rest of the way, right? You could use that power reduction formula and, anti-differentiate on that. What I'm going to do instead is I'm going to use a calculator. Make this go a little faster. Pi divided by 2 cosine of theta, square it with respect to theta, 1.57. Wait a second. That's pi over 2, right? So say that's equal to pi divided by 2. 27 and 33, an improper integral. That's good. Good that you get reminded about those. Okay, the improper integral, 1 to infinity, 1 to infinity, 1 over xy dx dy. Okay, I'd have a whole lot more to say about this if you're in my actual multivariable calculus class, but I think for now I'm just going to leave it as is. Okay, an antiderivative for 1 over x times 1 over y might actually well, this is a constant, right? So I could factor it out. That's what some people would tell you to do. Okay, but I'm just going to say ignore it and just keep it there. Antiderivative for 1 over x with respect to x is log of the absolute value of x. Okay, so I've got 1 over y times the log of the absolute value of x as x runs from 1 to infinity. Well, that's equal to 1 over y times, okay, can't plug in infinity to log. That's the limit as x approaches infinity of log x minus log of 1. Well, that's infinity, so I don't even have anything. I guess it's like putting infinity into the integrand. That's not going to go well for you. This diverges. Okay, so this integral fails to exist because that limit doesn't exist. Okay, 19 through 25 odd. Use a double integral to find the volume of the solid. I think what I'm going to do on this one is I'm just going to set it up, and yeah, this is already taking a while. And if you're going to do this many problems, if you've done all the rest of them, that's plenty of double integration from my standards for after the AP exam. So I'm just going to say, all right, we're integrating. Oh, they even gave us the bounds. So this is it's a rectangular region in the plane. So this is like best case scenario. So this is going to be a double integral, 19. Double integral of y over 2, okay, as we'll say x runs from 0 to 4, and y runs from 0 to 2. Okay. And then I trust you would be able to compute that the rest of the way using the skills that you've just learned. Okay, number 21. Okay, 4 minus x minus y is the surface that we're taking the volume underneath, and y is running from x up to 2. Okay, now if y is going to depend on x, the variables can only go on the inside bounds of integration. I think for reasons that will become more obvious if you take the class. Okay. In this case, okay, y is running from x up to 2. X appears to also be running from 0 to 2. So this is going to be dy and then dx, because y is x and then 2, and x goes from 0 to 2. And then that's 4 minus x minus y. Okay, number 23, 1 minus xy. Okay, well, y is running from x up to 1, and it looks like x is also going from 0 to 1. So this would be dy and then dx, because y is what's going from x to 1. You can see it right there, y equals x up to y equals 1. And then the integrand is 1 minus xy. Okay. The last one, 25. Oh, an improper integral. Maybe I'll actually work this one, so you can see how an improper integral would can come back finite in a double integral situation. Okay, you can barely even see the height of this thing. So it's 1 over x plus 1 squared, y plus 1 squared. I could have drawn this a little bigger so it looked better, but whatever. Okay, 0 to infinity on x and y. All right. Okay, I'm just going to put dA because, okay, it doesn't actually matter, right? Yeah, it doesn't matter which order because it's got so much symmetry to it. Okay, so I will now jump in there and start solving this thing. Maybe I'll just copy the problem and zoom in. Yeah. Okay, an antiderivative for this with respect to y is going to be negative y plus 1 to the negative 1 multiplied by this. So times negative 1 over y plus 1 as y equals 0 up to y going to infinity. Okay, well now as y goes to infinity, this thing goes 0, and so I have negative x plus 1 to the negative 2. You can't even see any of that, pardon me. Divided by y plus 1, where y is 0. Okay, so this is going 0 plus x plus 1 to the negative 2 divided by 1. Okay, so now I'm taking the integral from 0 to infinity of x plus 1 to the negative 2 power dx. Right? Because all of that for the thing in y to just come back, well, 0 minus negative 1. So it's okay. We're going to anti-differentiate. Let x run from 0 to getting towards infinity. And then we're going to take the limit as x approaches infinity of negative 1 over x plus 1 minus negative 1 over 0 plus 1, and that's going to again be 1, and well, that'll be all for this problem, and I think that's all for this video. Thanks for watching.